Welcome back. Electroless deposition today. I'm hoping that's going to focus. What this is obviously not electrode deposition. If we had electrode deposition, we would have our electrode and we would make it probably negative, attract some positive metal ions to it and deposit some metal on it. But we want to do the equivalent but without having anything connected. Why do we need to do that? Well, we might want to do something good, like make a metal track on a printed circuit board, for example, or we might want to metallize something like this phone, which is glass, a mixture of glass and polymers that are metallized to make it look a little bit more valuable, but also to protect it. But we could also think of things like this here, which in part is a lighter, but in part it's metal parts. But there are also plastic parts that have been made to look like metal by depositing a thin layer of metal on them. The problem, as we will know from previous parts of this course, is that getting metal onto a polymer surface or onto a glass surface typically involves evaporating the metal through a vacuum, and that costs money. And so for large surface areas, for cheaper parts, and for going around corners, we need another technique. The standard technique is electroless deposition, and it works in the same way as electrode deposition, that we have a metal ion in solution and it's going to be reduced, but because we don't have an electrode, we don't have anything to make electrical contact to a piece of polymer, then we need to do the reduction in solution as well. So here's the standard setup. We've got our electrode that we want to plate. We made it negatively charged, and it is reducing some metal ions from solution to metal zero, which sticks on the surface. Electrons come from the electrode, they have to come from the power supply, and on the other side we're reducing, or we're oxidizing some kind of reduced form of some other chemical to an oxidized form, and that gives us some electrons. Typically we do this in the same bath, so in this case we might be making a metal on one electrode and oxidizing some water on the other electrode to make oxygen. We might also be making chlorine or dissolving a metal. So if this was a copper bath, we would be dissolving the electrode. We always need both reduction and oxidation reactions in our bath, even if we've got an electric power supply, but obviously the reduction potential of this couple and the oxidation potential of this couple, or the other way around, whatever you want to call it, don't have to be the right way round. We can apply some power from our power supply to get there. If we want to do electroless deposition or electroless reaction, we need our reduced form, so the thing that's going to get oxidized, our reducing agent, to be more reducing than the metal ions. Otherwise we won't be able to cause the reaction to go forwards because we don't have a power supply. But we then get stuck with a problem. How do we make the metal that's formed stick to the thing that we want it to stick to? We can get a little bit there by looking at the demonstration that I did with tin and platinum. You can look that up. If we take a piece of tin, it is reducing enough to generate hydrogen in a slightly acidic solution. But the overpotential for making hydrogen at the surface of tin is quite high. It's difficult to make hydrogen on tin, and so nothing happens. Platinum is exactly the opposite way around. Platinum has a rubbish overpotential. It's a noble metal. It doesn't really want to do anything, but it does have a high catalytic activity towards hydrogen, so the overpotential of hydrogen is extremely low on platinum. So if we put these two pieces of metal, they can be beads or any shape we like, into some acid, nothing happens. But if we connect them with a wire, then the reaction starts. So we have hydrogen forming here. We have H plus taking an electron and going to H dot, and two of them combine to form hydrogen. And on the other side we have our tin going into solution as tin 4 plus probably. So now we have a way to see why our reaction might not happen or might be located in a place that we want to. In solution, it's very difficult sometimes for reactions to happen, particularly redox reactions, but also other types of reactions, and so they go comparatively slowly or not at all. They can then work far better on a conducting surface, because then the reduction reaction and the oxidation reaction don't have to take place at exactly the same place on the surface. Conduction along the surface is fine, so we can do it in 2 places. The other part comes from what you will have had in colloid chemistry perhaps, where if we take a particle and we make it smaller and smaller and smaller, the effect of the surface becomes larger and larger and larger compared to the effect of the bulk material. If we consider trying to make very small particles, we have to start with a few atoms, combine them together to make a particle. So we're imagining the metal is trying to form in solution and form a metal that's not soluble in water or organic solution, probably water, and it will eventually fall out. That will be the problem. We don't want that to happen in this case. But we have an advantage, that generating a new particle is difficult, because a new particle has a very high surface area to volume ratio, so it is comparatively difficult to do that. And if we look at the process, we can see that we've got the Gibbs free energy is equal to delta H minus T delta S. It's the same as always, but when we do this for bulk materials, we ignore a term for the surface energy, the Gibbs free energy of the surface, and that is comparatively large for starting the particles off. We'll now look at it in a different way, as if we were going to take a solution and make it more and more concentrated and cause something to precipitate out. So if we imagine we take a solution of something like silver and we add chloride ions to it. When we pass a certain point, we will cross the solubility product, the solubility limit of that particular compound in our solution, and we thermodynamically will start to make particles. But in practice, we won't really make particles. And if you recall, in thermodynamics or in physical chemistry, we did the same thing. We cooled down some water and we passed 0 and nothing happened. It didn't turn into a solid until it had passed 0 considerably, and then it came back up in temperature to 0. Exactly the same thing happens here, and it's for exactly the same reason, that it costs surface energy to make a new particle, but it doesn't cost surface energy to grow a particle, because the surface area is replaced by less surface area per unit mass. So here we are, increasing our concentration. When we pass the solubility limit, nothing happens, and we make it supersaturated, and we can keep going, and then at some point we reach and we make it unstable enough that it starts to form particles. So we get a burst of nuclei formation, and then the concentration of our solution will come down, but it won't go past the solubility limit, because then it would obviously dissolve again. So then we will have some kind of approach to the solubility product where we would be at a stable situation thermodynamically. But we don't need to be at a stable situation thermodynamically any of the rest of the time. If we look at the number of particles that are formed, we can see that nothing happens, and then a lot of particles are formed. Maybe some more will be formed up for a little while until it passes some other threshold, and then no more particles are formed. It is possible that particles collide with each other, so we end up with less, so we might see a decline as well. It depends on the conditions entirely. If we look at the size of the particles, obviously it's undefined until this point, and here, after this point, they're growing. Here they're very, very small because we're making new ones, and then we stop making new ones because our concentration has now dropped and we're just growing them. In the same way that when we had water and we were freezing it, we had liquid water, liquid water, liquid water. It's obviously the other way around in that case. Then we start to make ice crystals. We make a few ice crystals and then they all grow. Once they've started to grow, the chances of making new ice crystals is lower because we can easily deposit water onto the surface of the ice that's already there. This is the same case, but we're doing it in solution, and now we have a different factor for where do the ice crystals go, or in this case silver iodide crystals, or in the case that we really want to do, metal. So if we imagine this situation where we've got the electrode potential and we're going to bring it down, then we will have a similar condition, which would be the redox potential of our metal, where we would theoretically start making metal. But if there's nothing for it to stick to, if we don't have a surface already there, then we can pass that position and before we start to make effectively particles in solution. So what we want in our solution is a reducing agent that is somewhere in this region but not too far down so that it makes particles on its own, because what we want for our electroless deposition bath is to put the metal onto the surface of a solid that's in there, and the driving force for it to choose to go on the solid that we want is going to be the surface energy that we would need to make new particles or to coat something else. But we can also help it a little bit further, and we usually do that by putting some crystals, some seed crystals of metal on our surface first. So what we can see here is that ideally, if we want to coat something rather than to make new particles, we should stay as close to this solubility limit line here, or in this case the reducing potential just to make the metal, and we can see that if we even make particles. So what you will see is if we have silver plus obviously, and we want to make silver 0 nanoparticles, then we have to make them fast because we have to pass this nucleation point. We have to pass the saturation point and pass the nucleation point very quickly so that we make new particles, and we want to get back very quickly to our equilibrium. So we reduce it with something very strong like sodium borohydride, which brings it right down here, and that will obviously cause it to pass this point here where it will generate new nuclei. If we want to grow those particles, then we can take them out and put them in a second solution which contains a weaker reducing agent, which could be ascorbic acid, vitamin C, or citrate. And citrate is a pretty crappy reducing agent, and it will be somewhere around here. And then it will cause the silver particles to grow. So if we want to make silver particles that are all the same size, the typical process is to first of all make a whole load of nuclei with this process here, and then to grow them with this one here. Obviously we don't have to use exactly these processes, but similar ones are used to make silver particles of standard size. Otherwise, if we use just citrate, we pass this very slowly and we generate some particles, and then we carry on generating new nuclei, and we also make big particles and small particles, and we have very little control over how many nuclei form because we're not passing very quickly, which means that any random differences in the solution will cause us to get more or less particles. I said particle a lot, I know. I hope that's understandable. So here is the reaction at a silver particle. It's easy at a silver particle. The citrate anion is oxidized. Is oxidized to acetone dicarboxylate plus carbon dioxide, so a CO2 group is split off the citrate anion. That is relatively complicated to do, so it requires lots of moving of bonds and things, and so that is easier at a surface where we can form temporary bonds to the surface. and in another place on our silver particle, silver is reduced. You can see that this is very much the same as corrosion, but it's going in the other direction, and it's also the same as a normal electrochemical cell. We've got electrons flowing out of the citrate through the metal and into the silver, making the silver into silver zero, which causes a silver particle to grow. This is exactly what we want to happen at our surface, and we might even do it with silver. So if we imagine a process where we're trying to electrolessly deposit silver onto some glass or something, we would have, first of all, some palladium particles. That's the typical catalyst for this. They have to be stuck to our silver, and we will have, stuck to our glass, our non-conducting surface, and our silver ions are in solution, and also the reducing agent, which we will call citrate in this case, but it's not necessarily citrate. It needs to be a reducing agent that brings it just reducing, but is also complicated enough that it's difficult for it to occur in solution. Because it's difficult to occur in solution, we can't make new silver particles in solution. Typically, whatever we do in a modern plating bath, they are stable enough that they will last for a reasonable amount of time, as long as there is no palladium in the solution. Likewise, we need to protect the walls of our container, because we don't want those to get covered with silver either. That will be expensive. We would lose the silver from our solution, and we would make everything dirty. We'd have to clean it. So to avoid that, there are other ions in there and other agents to ensure that we don't deposit so much on the walls. In this case, it's typically lead ions and complexing agents that stick to the surface. The more important thing for our particular topic is what is going to happen here, because out of interest, the silver is going to start to deposit on our palladium particle, and it will increase in size, but it needs to lower, or it doesn't need to, but one of the driving forces is minimizing surface energy. And one of the ways it can minimize surface energy is to grow along the surface, as long as our glass, in this case, is high enough surface energy that our silver can stick to it and it doesn't cost too much extra. Growing out into solution will generate new interfacial area, and that obviously comes with a cost of surface energy. Typically, making metal surface area is costly in surface energy. Metals have a very high surface energy, and therefore it is less likely to do that unless we have excess energy in our bath, and we don't have that because we've deliberately just nudged it. We've just nudged it past its reduction potential, and so we're going to typically grow along the surface, and if we've got it right and we've got enough planarizing and other agents in there, we can generate a flat film on our surface eventually. That is what we would want to do. If we've got a polymer, we may have to treat it beforehand to make it stick to the metal and to make this process energetically favorable for it to grow along the surface rather than to grow out into solution or just make these particles really big. Obviously, a high surface energy of our substrate also helps to make the silver, in this case, stick to our substrate, which is good because that's what we're trying to do the whole time with this process. We want to make something look like a metal, but it isn't. A typical use for this process would be to make circuit boards or to make a kind of microchip devices. So we want to connect different layers in our device together with some kind of wires, and ideally for that we would want to use copper wires. The reason that we want to use copper wires is the combination of price. Copper is cheaper than silver and gold, and conductivity and non-reactivity. The good thing about copper in this case is that we don't have to hit it too hard to make it reduce, a little bit harder than silver. And the reason for that is that there is another problem that we will come across, that the air will tend to oxidize the either the surface as we're making it, or the reducing agent in solution. It will be a competing reaction and we will have to deal with that in some way. Typically, oxygen from the air will be an issue, but we will not get, from our Pourbaix diagram, we will not get to a low enough reducing potential to reduce the water, because the reducing agent is never going to be that strong. We will fail to do that with any of the metals, or we'll fail to do electroless deposition in water with any of the metals that have a lower reducing potential than water, because then everything won't work, because we need to get so close to this just depositing condition. So now we have the next problem, which is how do we get the palladium onto our surface, or whatever initial metallization that we need to cause it to grow. It doesn't have to be a complete film, as we just noticed. It can grow across the surface, but we do need to have a reasonable coverage of particles of palladium or some kind of catalyst on the surface to get it to go. They don't necessarily have to be super well attached, because the film will grow underneath them as well, but they do have to be there, and they have to be attached enough that they don't fall off in the bath and cause new problems to occur. So the new problem that we have is we need to attach these palladium particles to the surface, and we have to do that without having any precursor particles. So we don't have any of the advantages, or not all of the advantages, that we had in the previous step. We're going to have to put them onto a clean glass or plastic surface. So we're stuck with several methods that we could possibly do that. Let's start from the bottom. So we could do an electroless deposition, but we're going to have to hit it harder. We're going to go further past the reduction potential to allow it to generate particles where it wouldn't normally do so. That means that if we do that, our electroless deposition solution is not going to last. We can't store it for any period of time, because it's going to be active and generate particles in solution on the walls of the container deliberately. We can, however, just accept that we're going to make particles and start off with particles. If we do that, we have some particles in our solution. We generate a colloid, some metal particles in solution, and we allow them to stick to our surface. That would happen first of all by electrostatic interaction, so we can make our metal particles positively charged and our surface negatively charged typically, and then we attach them, so we interact them electrostatically, and then we would have to make them stick more permanently. That is easy to do. All we have to do is dry the solvent, and that causes our particles to get very, very close to the surface, and then it is more difficult to remove. Or we could, of course, do the easy way and evaporate some metal onto the surface. We don't need very much, because it doesn't need to conduct from one side to the other anyway. We just need single particles, so we can just give it a little bit to dust the particles on the surface. We could also evaporate something else. So if we take an equivalent process for making carbon nanotubes, we can evaporate a metallo-organic compound to make a layer, or we could just paint it on, and then we can reduce it afterwards to the metal, in that case in a hydrogen environment, but that's because we've got money to do so. And we can go to high temperatures. In this case we might have a polymer as our substrate, so we don't want to go to high temperatures. We can't heat it up too much, and we don't want to go to violent solvents. And so ideally we would stick with some kind of colloidal attachment, which is the easiest way to do it. So a quick excursion into colloid chemistry. If we have a tin silver particle, which might be what we're going to use, it's one of the proposed ways of having a cheaper catalyst that isn't palladium for making copper surfaces. We make it positive by either having a positively charged surfactant at the surface, or simpler, we have an excess of metal ions. So we have our tin silver particles in a silver solution. The silver ions will interact with the surface and make it slightly positive. Our surface could be glass, and glass is naturally negative in most pHs. Obviously, if we make it really, really acidic, we will make our glass positively charged by absorbing hydrogen ions to it, but we don't want to do that. Our silver will be reasonably stable in most pHs. We obviously can't go too basic because then we'll drop out silver oxide. If we take our positively charged colloidal particle and we interact it with our negatively charged glass surface, they will approach each other, but they can't actually touch because both of these surfaces are hydrated. There's a water layer on the outside of the particle and there's a water layer on the surface of our glass. Likewise, if we have a surfactant in there to make this positive charge, that would also be in the way. It will be stuck on the surface of the particle, making it positive, but it would also be in the way and block the two metal, or the metal and the glass surface, from interacting directly. In solution, that's the best we can do, unless we do some tricks, but that's what we're going to get to typically. Then we can take this out, and this is actually attached, but if we wipe it, this will come off. So we don't want that to happen. And the easy way to fix that is to allow it to dry. If we allow it to dry, the water in this gap will evaporate and the particle will touch the surface. Once it's touched the surface, the interaction will be between the metal and the glass, and they both have relatively high surface energies, higher than water. So once they've touched, water can't get between. Before they've touched, we can't get the water out, but once they've touched, the water can't get back between, and so now it's stuck on the surface. There's only a small interaction sort of area, because it's a spherical particle, so there's only one effective point position where it's touching, but obviously in reality it won't be quite so, it won't be quite such a perfect sphere, so it will distort, but that's not a problem because we're going to grow copper in this case from the outside of it, and as long as that binds to our surface, our crime of not having a very well attached catalyst particle will be covered up fairly quickly. Then we'll have a metal layer on our surface and everything will be happy. If we have a polymer, we have to get to this state beforehand, which takes us back in this row of, or in this course, it takes us back to corona discharge and plasma treatment of polymers, where we can graft hydroxide and acid groups to the surface of our polymer, which will make it negatively charged, as long as we control the pH. This is the approach curve of a positively charged colloidal particle to a negatively charged surface. As we can see, it's attracted to the surface out here at far distances, but not very much, because obviously the further a charge is away from a surface or another charge, the less the interaction. As we bring it up closer, we get down and down and down, and we get to this secondary minimum where there's water in the way, and on its own it can't beat this energy barrier, which would be squeezing the water molecules out of the gap in between. If we manage to beat it in some way, so typically with an atomic force microscope we just push. In this case we are drying the water out, so we're using a different way of getting rid of these molecules that are forcing it apart. Then it can drop into the primary minimum, where the two surfaces interact directly. So this is where, as we approach, we get closer and closer, and the metal ion atoms interact with the silicon and oxygen. When we push it any further closer, we're actually distorting the bonds in the material, and so that's obviously going to generate a repulsive force very, very quickly, and that's what this piece is. If we had like charged surfaces, this would be, so all of this would be up here and it would decay down, because obviously there's a repulsive force, a repulsive electrostatic force, but we would still have a primary minimum where the atoms are interacting with each other, but they obviously would repel at most distances. Once we get close enough, however, they will stick. Okay, that's enough on electroless deposition. You can look it up. I'm going to put a link in the video description and also somewhere else to a discussion on it. It's a very interesting technique and very useful industrially.